streaming. Let's see if this is streaming. Hello everyone, just an update on things. Did the oscillator and it's actually working. So powered by the cells here and feedbacking it through the secondary, keeping it going. And it's actually steady. And it's saying 883 kilohertz. So this is actually RF. So let's find it on the AM. 886 it says. There it is. 91 dB. 890 kilohertz AM. That's what you're seeing on the scope. So the yellow here is the Joule Thief oscillator on the feedback loop here. So it's peaking at 16 to 18, and the blue one here is the secondary, which has a diode feeding back into the cell. So it's actually in phase. It's hard to see there, but the input and output, if that makes any sense, one is reinforcing the other. And it is a sine wave. Just trying to you can see that. This is the oscillator, and over here, which is more like a triangle, it's the secondary pickup, which is being half rectified with one diode back into the cell. So the trigger is cleaner because I've got the diode there rectifying it, and it does emit a field. So here's my field meter. I'm going to shove that right in there in microvolts per meter. So 133 microvolts per meter, and then quickly diminishes to like 12 over here, and then ultimately nothing over here. So radiant it is, and it is essentially powered by its own electrostatic potential. So we're getting RF at around 860 kilohertz, which means it's friendly for coupling with antenna-like systems and coils and loops and that sort of thing. So what you're seeing here is the secondary pickup, which is damped down to 3.7 volts because it's feeding back into the cell/capacitor here. And what we can do from this point on is we could use the secondary. I'm not there yet, but this could be our trigger to dump. Got a little capacitor here. You don't see it, but it's not doing anything. It's just charged with these oscillations. But my whole idea is to have another transistor because there's not enough power to do anything more, but through the field, through the secondary, since it's not coupled directly, it's like RF, right? It's like another radio listening to the station. I'm going to use that as the trigger for the second transistor to control the cap dump into a transformer, kind of like this, but we're going to make the primary loop high Q so that the capacitor doesn't short out right away, and the high voltage over here is going to be our potential well. So our free way of getting like our 1000 volts out of just pulsing these cells, and pretty well self-triggered and everything. I'm trying to keep everything simple, right? So pardon me if it seems very primitive and basic, and oh, someone's going to comment, it's only a Joule Thief, it's only, yeah, well, the point is, these are powering it, right? And it's not a typical kind of power cell. Being an electret, it self-regages at every pulse, so it makes up for the loss and then amplifies itself, right? But naturally, like this, there is a limit. So what I want to do is, again, I, and what I'm saying is it's wasting this right now. It's shooting RF in the air. I'm charging a capacitor with it, but I don't have a mechanism to dump that and step it up some more. So my idea was to use the field dynamics as much as I can so I don't actually have to load the physical circuit down and switching and then bog everything down because you don't really have a lot of current, but you do have potential. And it does drive transistors just fine. So yeah, I just wanted to show everyone that because I did go live earlier today, kind of explaining what I wanted to do with the power cells here. And it's a shame. I see if I could show the view better here. This is the scope, and this is the two waveforms I'm talking about. The oscillator and the secondary being fed back is more like a triangle wave. But it's these power cells running the whole show. I'm feeding back into that. Just trying to get my angle here. That's too much on this side. I gotta go more over here. Takes forever to readjust the view, right? No. Okay, so more like this. Let's see. No. Okay, I guess people are asking questions. These are, I've been working on these power cells for about a week now, different solid state electrolytes and dielectrics and electrets, basically, more electrets. So I've been testing them because the whole idea is to have one run an oscillator, and then the oscillator field can be used as a trigger to dump the cap from another collector from the, you see, having all of these field couplings doesn't interfere with the circuit as if it were all directly electrically looped, you see. These things don't offer, it's more of an electrostatic thing. They offer a couple volts, but 1 milliamp or less. It's not a current thing, it's an electrostatic. So every time I try and load it with more than one transistor, the whole thing stops. So my clever idea was to use an air coil like Don Smith to make a flyback or a joule thief kind of oscillator, and then use the secondary to feed back and control a second transistor without bogging down the system over here, which could then cap dump. I have a little capacitor charging from the field over here. I'm not doing anything with. It's right here. See? And it could be any capacitor. I just put this there to have a somewhat of a capacitive effect. And then the second transistor would be driven, the base like a switch from the secondary pulse over here. And then that could switch into a high Q coil like this here. And this high voltage here into a high voltage capacitor, and then on it goes, and you can build up your current that way. So yeah, so that's the thing. Not enough current to run multiple anything fancy here, but it always runs one transistor. I've never had problems with that. So this is where I had the idea. Take the secondary, which is the blue one over here, and use that as the control trigger. It's not electrically coupled anymore. It's like an antenna because it's an air core. It's like Don Smith, and it's running at RF, 860 kilohertz. So you can play that kind of a game now. So then I could use the field of my trigger right here to actually pulse the second transistor without it being directly, there's no impedance load is what I'm trying to say from it. And it can operate like a regular switch and dump my capacitor into the high Z load, and then I can continue on like that. So what I have right now is I have it rectifying and feeding it back into the cell, so it's reinforcing itself essentially. It basically it should run quote unquote forever like this because it keeps regauging itself. But we're wasting the field. We're getting saturated with a lot of RF. There's not a lot of pickup systems here. There's just one coil that I'm using, and I'm not doing anything with it. But you can start doing stuff with it. But it's just to show you that it's Tom Bearden's. You create a potential. You you pulse it high Z so that you don't collapse your dipole essentially, and then you build up a high potential, and that becomes your gradient, and the gradient difference is what powers your last stage, your load, or your you can create a new pulse through a coil or something, transduce it to whatever you want, but it's that gradient's difference. So it's about trying to build it up, right? So this way here, you can do it at high frequency and with resonance and all of that, which just isn't really fine-tuned or anything. It's very quickly. What's saving our bacon right now is because these cells can make up for the loss and provide more because they regauge every pulse. Now, normally speaking, the cell wouldn't be kicking itself back like that because there's no mechanism naturally to do this. But if you're taking like one impulse from it, sending it through the system and amplifying it and kicking it back, and it's ready to give you the same amount of current for the second pulse, but now it feels a little bit more potential, there's your gain mechanism right there, and you're letting the environment essentially do it for you, right? So again, just something I had in mind, which so far looks like it's going to work. Um, it's emitting a field, it's emitting RF. I've got it feedbacking into itself. And right now, no switching mechanism to collect the cap dump, but that would be next. So it's the whole idea of the gradient difference and finding a way to give you that. You want to use the environment, nature, whatever you want to call it, to set up those conditions, that gradient difference. And once you do that, you use that to power your load. But there's so many ways. But optimally, if you can find a natural mechanism to trigger that system, you want to go with that naturally because it's just, why run uphill when you can run downhill, right? I mean, so yeah, this is an example of using a natural system, which obviously doesn't violate the laws of physics or anything like that. I go back like almost 2 years now with all these power cells, so I have a pretty good idea of what they do as an electret, what they do as a capacitor. Um, Not very good batteries per se. If you think you can charge it, through a 12-volt charger and run your car with it, it's not that kind of a power storage device. It's an electrostatic effect, which 99.9% of people neglect because they figured that because it's electrostatic, it's not worth anything. But again, that's all you need to set up to start the system anyways, and then let it roll downhill, right? Like we're doing here. So, very interesting just to experiment with it, even on a small scale, because it gives a good understanding. And here I am that I've been talking all this time, and it's still running. Never had to put any additional energy into it. It just conditioned itself, and now I'm keeping it going with the feedback. And now, of course, it's an open system, right? Because not only, but this is RF and it's very loosely coupled. So what happens is all of this is acting like one big antenna at the same time. We kick-started a process, but if there are fields nearby, of course it's going to take some of that in. It might not be optimally tuned, but you can't say, it's not going to take anything from the environment because it's set up as an open system. But that's fine, we're not breaking any rules. We just have to acknowledge that, yeah, there are usually wasted components from high-speed switching and 60 hertz and all that. But you're not just limited to that. You've got all of the earth fields, the environmental energies, the Earth's electrostatic potential difference, the 200 volts per meter square. I mean, there's many avenues here to go to. But whatever we can get, I mean, it's that more that, I personally didn't have to go like in a store and buy in a battery like this and inject into the system. It's using itself, it's amplifying itself, and it's also coupling to whatever may be nearby that could help it. But with that said, there's also such thing as if the wrong frequencies are being triggered at the wrong phase, there's also the destructive interference. So if you're near, let's say, where there might be like near a communication hub, cell phones and radios and all that, there might be so much crosstalk there that it may actually linger the system instead of help it. So, I mean, it's all about, I guess, fluking it when you try and I like the idea of making RF antennas, but it's not very dependable because you are depending on literally man-made devices. It's better to try and tune for artificial, sorry, what I'm trying to say is natural phenomena, like sorry, tongue twister, currents, earthquake energy, lightning energy, that sort of thing, and have capacitive couplings and whatnot. So you don't have to say, well, it's a quote-unquote human-generated source, because there's always people that will scrutinize and say, well, it's not free energy, it's just somebody else paying for it, But needless to say, that can be tweaked and fine-tuned anyways. So, yeah, here it is, still working, oscillating at, right now, see, it's charging itself, so we're up to 960 kilohertz. So essentially what happens is the more energy the system accumulates, because this is a free-running oscillator, it goes faster and faster. When it starts to discharge, the frequency starts going lower, and next thing you know, it's at 300K. Then it's at 100K. That's an indication I know it's about to clonk out, and then 50K, and then finally, maybe a minute or two in the audio range, and then it's out. But when it's going up like that, it's an indicator that the system is actually accumulating energy as we're talking. And the frequency is increasing, which means so is its efficiency, because more clicks a second, because I'm feeding it back. So you see the potential is rising, and it's supporting a faster frequency. 996 now. So I'm going to get into the 1K there. Sorry. Yeah, 100K, sorry. I'm in the AM band now. So 990 some K. So 1 megahertz. We're almost at 1 megahertz. So that's pretty fast. We started at 620K. And just from this talking, we're almost at 1 megahertz. So it is accumulating spikes in this configuration and running faster to compensate. So that's a thing too, which is saving us too from getting into total chaotic mode. The oscillator just makes up for the extra energy by running faster. But there is a certain point where, especially with a sloppy circuit like this, that at around, maybe 5 megahertz or so, there's going to be too much parasitic capacitance and everything for it to be stable. But again, just a proof of concept to show people that pretty well works. And yeah, again, I'm gonna cut it all short for now, and I will see you next time. I just wanted to show this because I know people are interested in this. And with that said, have yourselves all a great day. And again, thank you for watching.